Hi, welcome to the National Electronics Museum. This is part one in our new STEM Spark series about videos concerning things in electronics. The first one we're going to do is a piece on the microwave oven. Do you ever wonder how you can look inside the microwave oven and see your food cooking? Light passes through the microwave oven, but microwave energy does not pass through to harm us. Why is that? To understand how we can look in the microwave oven, we need to go back to the experimental work of Heinrich Hertz in 1887. Hertz looked at radio waves and visible light and determined that they are electromagnetic waves. Now, 20 years before Hertz, a fellow named James Maxwell looked at electricity and he looked at magnetism and realized they were part of the same thing. And when combined together, they travel in waves. Now, he did this using only math. It took Hertz 20 years later to develop the experiments that show that Maxwell was right. And these famous mathematical equations that Maxwell came up with are called Maxwell's equations. Now, electromagnetic waves travel in a particular direction at the speed of light, but there's a component, an electrical and a magnetic component between them. Sometimes they're vertical, sometimes they're horizontal, or sometimes they're any angle in between. And that's going to go and show how we can explain how we can look in the microwave oven. So one way to reflect an electromagnetic wave is to have a conducting material, that is a material that can conduct electricity, in the same direction as the polarization of the wave. So if the wave is polarized in the vertical, we can stop that wave with vertical strips of conducting material. The distance between those conductive strips have to be some percentage of the wavelength of the wave. So we're going to demonstrate polarization with this fairly simple experiment. On this side, we have a feed horn, which is going to transmit microwave energy. And on this side, we have another horn, which is going to receive the energy. We have a gauge over here that measures how much energy we're sending, and a gauge over here that measures how much energy we're receiving. And in between, we have those polarized strips of wire. What I'm going to do is rotate this, and you'll be able to see the difference on the gauges, whether all the energy is going through or only a fraction of the energy. Okay, what we have is the transmitter is now transmitting microwave energy. It's going through the screen to the gauge over here. And you'll notice it's close to 150 microamps. So a lot of the energy is passing through our screen. That means this is vertically polarized, and we know that because I'm going to turn the screen vertical. Notice very little energy is now passing through the screen. Back to horizontal, the energy goes up. To vertical, the energy goes down. Now, how does this work on the microwave oven? Okay, so now we're back to the microwave, and you'll notice the microwave has a screen, but it's not like the screen on the polarization experiment. Here we have both vertical and horizontal conducting elements. Now, remember what I said before is that polarization can occur in both the vertical, horizontal, or some angle in between. By putting lines straight and from side to side, we're blocking both the vertical, horizontal, and any of the angles in between. So that microwave energy cannot escape through the door. Okay, now I know what you're thinking. You're saying, hold on for a minute. You said light is an electromagnetic wave, therefore it's polarized. How come light can pass through here, but microwaves can't? Now here's the answer. Even though both light and microwave energy travel in waves, the size of the wave is what makes the difference. The microwave waves are about 13 centimeters. So you can imagine them being about this big. Imagine a wave going through the ocean. From crest to wave to crest to wave is about 13 centimeters. However, light travels at a wavelength over 1,000 times smaller than the microwave. So that means these holes are a small percentage of the wavelength of the microwave, therefore the microwaves are blocked. But the wavelength of light is so small that it can pass through the holes in the microwave without being blocked by our conductive strips. All right, there you have it. That's why you can see your food cook, but the microwaves don't cook you.